I'm going to show you a card trick which seems completely impossible, but which we'll then see is not only possible in theory, but is in fact completely doable in practice, and it's only going to take a sprinkle of math. Of course, to demonstrate this incredible trick, we will need a deck of cards, although perhaps I should get a different deck. Here we go. These are much easier to see, although on second thought, they're a bit grotesque, aren't they? Okay, here we go. This is gonna have to do. So, we have a magician, and he has an assistant on stage. The magician has presented a deck of ordinary playing cards. The assistant takes the deck of cards, shuffles them up very thoroughly, and then strides out into the audience. 5 audience members randomly select 5 cards from the deck. Of course, the magician has no way of knowing what any of these 5 cards are. And since the magician is completely clueless, the assistant gives him a hand and reveals 4 of the 5 chosen cards. And the magician knows, after seeing the 4 of hearts, the 6 of clubs, the 5 of hearts, and then the 6 of diamonds, that the 2 of clubs is the secret card. Of course, if you've lived a life of days in which you've observed reality, you would be none too quick to trust the genuineness of the magician and his assistant. Surely something duplicitous is afoot. Maybe there was a hidden camera which was actually attached to the assistant and saw the cards being drawn, or perhaps the deck was not an ordinary deck after all. There's any number of non-magical explanations for how this trick could be performed through actual trickery. But could we possibly concoct some way that this trick could be performed genuinely? Well, if it's genuine, the only communication that the assistant has with the magician is revealing those 4 cards. And in fact, there's quite a bit of power in revealing those 4 cards. In the same way that in language, different sequences of letters correspond to different words, the magician and assistant could have an agreed upon system with these 4 cards, where different sequences of 4 cards correspond to different individual cards, thus cluing the magician into what that 5th card actually is. So then perhaps the trick is possible, although with some math we quickly find that this is not at all a plausible solution, because if we're ordering those 4 cards that are revealed to the magician, well, there are only 4 times 3 times 2 times 1, or 4 factorial, ways that they could be ordered. That's a total of 24 different sequences. This simply cannot work, because an ordinary deck of cards has 52 cards. So if 4 cards have been shown to the magician, there are 48 other cards which haven't been revealed, and all of those could potentially be the 5th card, which means these 4 cards would need to be used to construct at least 48 different sequences, so that every one of the possible remaining cards could be identified with one of those sequences. But given that 4 cards can only be used to construct 24 total sequences, clearly this is just not possible. But there is still a little bit more power for communication that the magician's assistant has. The magic is in that 5th card. Not only does the assistant have the choice of how to order the 4 cards that he reveals, he also has 5 choices for which card should be kept secret. So then let's start sketching out a diagram to represent this situation. On the left, let's put a set that we're going to call X. The set X is going to contain all possible sets of 5 cards. Of course, this set will be very large. There are many different ways of selecting 5 cards from a standard deck of 52, but just as a couple examples of the sets of 5 this set would contain, this set of 5 contains the Queen of Hearts, the 6 of Spades, the Queen of Spades, the Ace of Diamonds, and the Jack of Clubs, and this set of 5 cards contains the Queen of Hearts, the 6 of Spades, the 7 seven of clubs, the ace of diamonds, and the jack of clubs. Now, our idea is that we're trying to construct a connection between sequences of the 4 cards revealed and these possible sets of 5 cards, so that when the magician sees a particular sequence of 4, he will know what the 5th card must be by identifying the sequence with a particular grouping of 5 cards. So we need to consider this other set that we're going to call Y, and Y will contain all possible sequences of 4 distinct cards. Of course, just like X, the set Y of 4 card sequences will be very large, but now we're going to imagine that this is actually a graph. A graph is a mathematical structure consisting of objects and edges that join them. In this case, we're going to join an element of X with an element of Y if the 4 cards in the sequence of an element of Y is in the collection of 5 cards in an element of X. So for example, all 3 of these sequences, which are just example sequences in the set I've written out, would be joined by an edge with this collection of 5 cards, because all 3 of these sequences only contain cards that are in this collection of 5. So I could draw these 3 edges joining those objects. Note that every other set of 5 cards that contains the 6 of spades, queen of hearts, queen of spades, and jack of clubs would also have edges going to that sequence, and indeed there are many other such sets of 5 cards. Neither of these first 2 sequences would be joined to this collection of 5 cards, because these 2 sequences both have the queen of spades, which this collection of 5 cards does not have. However, this collection of 5 cards would have an edge to this sequence. The 4 cards in this sequence are all contained in this collection of 5. Again, both of these sets are very large, and what I've chosen to write out explicitly is just for the sake of exposition. But there are many sets, many sequences, and indeed many edges that are in this graph which I've not drawn. But it's apparent upon observing these 2 edges from different collections to the same sequence that it will not be a trivial task for the magician to assign sequences to collections of 5 cards. The assistant could reveal a queen of hearts, a 6 of spades, a jack of clubs, and an ace of diamonds, and the magician, of course, would not know what the 5th card is. This sequence of 4 could correspond to this collection of 5, in which case the 5th unrevealed card is the queen of spades, but it could just as well correspond to this collection of 5, in which case the 5th unrevealed card is the 7 of clubs. So what we need to make this trick tenable is what graph theorists call a matching, which is a set of edges with no common endpoints, so that every single collection in X is matched by an edge to exactly one distinct sequence of 4 cards in Y. For a simple example of a matching, suppose we have a town consisting of 3 women and 5 men. These dots are what we call the vertices of a graph. The women are represented by the 3 pink dots, the men by the 5 blue dots. We're going to join 2 vertices, that is a woman and a man, by an edge if the woman likes the man. And perhaps in this quaint little village, this situation of romance appears as follows. And then suppose we ask, is it possible for all of the women to marry so that they are happy with their husbands? And indeed, it is. The solution to such a problem would be a matching. By picking out a set of edges that have no common end vertices, each woman is able to marry a man that she is happy with. We've then matched these 3 distinct women to these 3 distinct men. Of course, in this situation, we end up with a couple bachelors, but no big deal. That's also not really relevant in our situation. It's okay if we don't use every single sequence in the set Y, but it does need to be the case that every single possible collection of 5 cards corresponds to some sequence of 4. So the question of the theoretical possibility of this trick becomes very simple. It is, does this graph have a matching? If there is a matching, then in theory the trick is possible. If each collection of 5 cards is matched to a unique sequence of 4, then the assistant can directly communicate the 5th card to the magician by revealing the correct sequence of 4. And thankfully, there's a pretty straightforward condition to check that tells us whether or not a graph has a matching. It's called Hall's condition, and this is what it says in the context of the marriage situation. Hall's condition is that every subset of women likes at least as large a set of men. So for example, looking back at this graph, if we look at a set of 2 women, like these 2 here, in order for us to be able to match them, they must like at least 2 men. And of course, since we were able to form a matching here, it's no surprise that condition holds. This group of just 2 women happens to like 1, 2, 3, 4 men. And of course, 4 is at least 2, the condition is satisfied, so there is a matching. I'll leave a link in the description to my video proving that Hall's condition forces a matching to exist if you're curious. Then, to show that our graph satisfies Hall's condition, we need to consider an arbitrary subset from the set X, and of course any arbitrary subset of X will be a collection of 5 card groups. To verify Hall's condition, we need to show that any arbitrary subset would correspond to at least as many sequences as there are 5 card groups in the subset. So let's start by asking this. Every single 5 card group in X will correspond to how many sequences in Y. This is the same as asking how many edges touch each 5 card group in X. Well, if we have a group of 5 cards, there are 5 choices for which card we could exclude from the 4 card sequence that it corresponds to, and for every possible 4 cards that we could use to make sequences, there are 4 factorial sequences that can be made with those 4 cards. This, of course, is 5 times 4 factorial, which is 120. So in fact, if we drew this graph in its entirety, every 5 card group in X would have 120 edges coming out of it, going to 120 different sequences that consist of 4 cards that all belong to the 5 card group. Remember that each 5 card group is connected precisely to the sequences of 4 cards that consist only of cards from the 5 card group. Now, the question we just asked about these 5 card groups, namely how many edges are coming out of each one, let's also ask about the 4 card sequences. How many edges are going to each 4 card sequence? Well, again, a deck of cards has 52 cards, a 4 card sequence has accounted for 4 of those, and so there are 48 other possible cards, and thus 48 different collections of 5 cards, which could correspond to any 4 card sequence. For example, in what we've sketched out, this 4 card sequence has an edge joining it to this 5 card group, where the 5th card that doesn't appear in the sequence is the ace of diamonds, but it would also have an edge connecting it to the 5 card group where the 5th missing card is the ace of clubs, and the 1 of diamonds, and the 3 of spades, and so on. There would be 48 5 card groups total, where this is a sequence that it's adjacent to. Okay, so every 5 card group is connected to 120 sequences, and every sequence is connected to 48 5 card groups. So now, let's say we've taken an arbitrary subset of X. We'll call it S, and this is how we write that notationally. So S is just some collection of the 5 card groups from the set X, and we're trying to show that this set S satisfies Hall's condition. Since S is an arbitrary subset of X, we don't know how many 5 card groups it has, but notationally it looks like this, with absolute value bars. This is read the cardinality of S. And together, we need to show that the 5 card groups of S are connected by an edge to at least this many 4-card sequences, at least the cardinality of S many sequences. So we may first ask, how many edges total are there touching the 5-card groups in S? Well, if S has this many total 5-card groups, and like we discussed, every 5-card group has 120 edges, the total number of edges touching the 5-card groups in S would be 120 times the number of 5-card groups. But then, how many 4-card sequences could these 120 cardinality of S edges be going to? Well, we know that every 4-card sequence only has 48 edges that go to it. So if we divide this count of edges coming from that subset of X, if we divide it by 48, the number of edges which go to each 4-card sequence, we will get the total number of 4-card sequences that the edges from S are joined to. Of course, 120 divided by 48 is bigger than 1, and so this is most certainly at least as big as the cardinality of S, and that satisfies Hall's condition. Said more briefly, what we've just shown is that if we take n 5-card groups from X, they will certainly be connected by edges to at least n 4-card sequences in the set Y. This means that indeed a matching does exist. So then the trick definitely is possible. The magician and assistant could agree upon a particular matching of sequences to 5-card groups. Then when the assistant reveals a particular 4-card sequence, the magician will know exactly what the 5th and final card is. Of course, you may wonder just how many sequences the magician and his assistant will have to memorize to make this work. Well, the magician certainly will have to memorize one sequence for every 5-card group. The total amount of 5-card groups is, we call it 52 choose 5. It's written like this with what's called a binomial coefficient. It's easy to calculate. It turns out to be 2,598,960. Okay, so I guess the trick isn't possible then, because there's no way the magician and assistant are going to be memorizing over 2.5 million 4-card sequences for a trick that is, although cool, certainly not worth that level of effort. But all is not lost. After all, structure makes molehills out of mountains of complexity. We need not just do rote memorization for over 2.5 million 4-card sequences. We just need to come up with the right system to convert 4-card sequences conveniently into 5-card groups. And the process of doing that is not nearly so hard as one might think. For this example, let's suppose that the 5 cards selected are the 10 of hearts, the ace of diamonds, the 10 of clubs, the queen of hearts, and the 7 of diamonds. The assistant, of course, sees these 5 cards, and by revealing the correct 4 of them in the correct order, the magician can make quick work of identifying the final secret card. The first thing the assistant must do is, among these 5 cards, select 2 of them which have the same suit, like in this group, the Queen of Hearts and the 10 of Hearts. So already you may say this method won't work if the group of 5 cards happens to not have 2 cards of matching suit. But if you know the pigeonhole principle, you would never have such a thought. If there are only 4 suits, and we draw 5 cards, guaranteed at least 2 of the cards will have to have the same suit. We then, in our mind's eye, envision this circle formed by the value of the different cards in the deck, the ace through the king. And the key thing we need to notice about this circle of card values is that any 2 values in the circle are within 6 clockwise steps of each other. For example, if we take 10 and the queen, like we have for the matching suits in this 5-card group, they are certainly within 6 clockwise steps of each other. Of course, if we regard the queen as the first card, we must make 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 clockwise steps to get to 10. However, if we regard 10 as the first card, we must make only 2 clockwise steps to get to the queen. Thus, using this method, once you've chosen those two cards of matching suit, the one which is to be regarded as first is that which is within 6 clockwise steps of the other. Having chosen these two cards as the matching suit cards, and seeing that 10 is the one that comes first, the assistant shall reveal the 10 of hearts to the magician first. And as you might have guessed, it is the Queen of Hearts which will be kept secret. So by revealing the 10 of Hearts, the magician immediately knows that the 5th secret card must be a card of hearts. The assistant then has 3 cards remaining to communicate the value of this 5th secret card. In particular, he needs to communicate the fact that the 5th secret card is 2 steps away from the 10 on this cycle. And like we said, on this cycle, any two values are at most 6 clockwise steps apart. So the assistant would potentially need to communicate any number from 1 to 6. So the assistant has 3 cards to communicate a number from 1 to 6, where that communicated number will represent the number of steps that need to be taken on the cycle to get from the revealed value to the value of the secret card. Well, this works great. We need to communicate 1 through 6, and we have 3 cards. You may recognize that 3 factorial is equal to 6, so it will be very easy to communicate any desired number 1 through 6 by using orderings of the 3 remaining cards. And the system, to be easily usable, won't be based on the individual cards at hand, but rather their values relative to each other. So we need an ordering on all 52 cards. The ordering within each suit is straightforward. The ace is less than 2, is less than 3, and so on, is less than the jack, is less than the queen, is less than the king. Then, to have a total ordering on all 52 cards, it only remains to order the suits as well, which we can simply do in alphabetical order, so that the clubs are less than the diamonds, are less than the hearts, are less than the spades. Thus, for example, a king of hearts would be regarded as less than a 2 of spades. And then a simple assignment of the orderings of relative values of the 3 cards to the numbers 1 through 6 completes the method. In our example, the assistant needs to communicate the number 2 to the magician, so he knows that the value of the hidden card is the queen, 2 clockwise steps away from the 10. To communicate that 2, he needs to reveal the remaining 3 cards in the order small, large, medium, just supposing that this is the arrangement he and the magician have agreed upon. Thus, the assistant will reveal the smallest remaining card first, which is the ace of diamonds. He will then reveal the largest of the remaining cards, which is the 10 of clubs, and then he'll reveal the one whose size was in the middle, which happens to be the 7 of diamonds. So, by revealing the 10 of hearts card first, the assistant communicated to the magician that the last secret card would also be a card of hearts. It also communicated to the magician to picture in his mind's eye this cycle and start at 10. The next 3 cards that were revealed, in the order small, large, medium, communicated to the magician that he should take 2 steps along the cycle, from 10, thus getting him to the Queen of Hearts, and clearly having the choice for the 5th secret card. Thus, this trick that may have seemed impossible at first, you and a friend could get a good handle of in an afternoon. Let's do one more example. Suppose the 5 chosen cards were the 5 of clubs, the queen of clubs, the 5 of spades, the 4 of hearts, and the 4 of diamonds. Then which card should the assistant reveal first? Well, you might think it would be the 5 of clubs, because that matches suit with the queen of clubs, and the 5 of clubs comes first. However, if we look at our cycle, that is not correct. If we reveal the 5 of clubs first, the queen is 1, 2, 3, 4, 5, 6, 7 clockwise steps away. That's not going to work. And so we realize the queen must come first. The queen is only 1, 2, 3, 4, 5, 6 steps before that 5. So if we have the queen first, we'll be able to communicate those 6 steps that need to be taken to get to the 5. So the queen of clubs comes first, and the magician immediately knows that the card we're looking for, which is going to be the 5 of clubs, is a club. The assistant then has these 3 cards left to communicate the 6 steps that need to be taken to get to the 5. To communicate 6, the assistant reveals the 3 remaining cards in the order large, medium, small. Remember, we ordered the suits alphabetically, so later in the alphabet is regarded with a greater value. So the 5 of spades would be the largest remaining card, and thus would be revealed next. Then the 4 of hearts and the 4 of diamonds, of course, match in the value of 4, and so we need to remember how we've ordered the suits, and since H comes later in the alphabet, it's regarded as having a higher value, so we would reveal that one next, and then the smallest, the 4 of diamonds, is revealed last. The magician then knows from the first card revealed that the secret card is a card of clubs, and he knows from the large, medium, small ordering of the subsequent 3 cards that the secret card is 6 steps away from the queen on that cycle of values, which thus gets us confidently to the 5 of clubs as the secret card. So there you go. That's how mathematics can make the seemingly impossible possible. And if you bust this card trick out at a party, probably a good chance you're gonna be just like one of these 2 men in the picture. Thanks for watching, and let me know in the comments if you have any questions. Be sure to subscribe for more of the swankiest math videos on the internet.
From my fate, twisting to escape this. Cutting out my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Embrace the tune of words and just how I say shit. And let me speak my poetry to your face. It's not intimate if you ain't listening. Not infinite if you ain't really into it.